Good morning, guys. I hope all you are well. Okay, let's start the session. So today we are going to learn about the splitting criteria of decision tree and few important concepts with respects to entropy, information gain, and a new concept called gain ratio. Okay, which will help us to understand how internally when we use a decision tree classifier in case of a classification problem, uh, the sklearn uses the entropy and how this entropy and information gain internally works to help us find out the best splitting criteria for the and give the best root node, the feature which has the lower entropy and the higher information gain, and that gets selected as the best root node. Okay, let us first understand the data a little bit. So this is the data. It's a very simple toy data where we are having features like outlook, temperature, humidity, windy condition, and a target variable where we want to say whether we are going to play or not basis this condition. Okay. In this session, and in order to simplicity for this session, what we will do, we will take one categorical feature that is that is outlook, and one numerical feature that is humidity. Okay. And we will to try to see between these features which feature should be selected as my root node. As we know, decision tree looks like algorithm is a very powerful algorithm, and it is also help us especially for classification. It is very powerful. It can be also be used for regression problem also, but in case of regression, decision tree is computationally expensive, and this decision tree is very robust. Okay, when I say robust, it can be used for any type of non-linear data. Okay, non-linear data. So decision tree does not require or does not have a prerequisite of any assumptions on the distribution of the data. You might have seen that other algorithms like linear regression and all, there are a lot of prerequisites or assumptions which need to be followed. So this is basically a non-parametric algorithm. Okay, it is a non-black box algorithm. What does that mean? That means it is easily explainable. That means when you try to explain the reason why your decision tree predicted yes or no, it is pretty explainable. Okay. In simple terms, we can say a decision tree is nothing but a nested if else condition or statements, right? So basically, we have a root node, then we have the intermediate nodes, then we have the terminal nodes that are the leaf nodes, where the leaf node are the terminal nodes where it has classified any one of the classes at its purest best. Okay, and decision tree will always go to the end depth. I mean, it can go to end depth, the maximum depth, so that it tries to classify each and every record correctly in the training data. And this condition, and that's why it can go to n depth. That means it can branches out. Ultimately, it is dedicated to reach to the n depth so that each and every record in the training data is correctly classified. Okay. This leads to its disadvantage. Basically, it is overfitted model. And we do several treatments like pre-pruning, post-pruning that we will discuss in some other class. But these pre-pruning, post-pruning are used to control the overfittedness. So basically, because of this nature of this algorithm, it is low bias and high variance. Okay. Okay. Let us see here what we have done. So pretty simple data sets. We have taken the class as a target and we are doing a label encoding. Okay. Once we have done a label encoding, okay. And then, as I said, the internal criteria which is used uh, to get the root node, the feature which will be used as a root node is based on two concepts. One is entropy, and on top of that, we find out the uh, information gain. So for entropy, entropy is calculated using this formula, which is pretty simple. Basically, it is the negative of summation of I equal to 1 to n, all the probabilities of positives and the negatives, log 2 of the probabilities of negatives and positives. Okay, with respect to the target column. So in our case, we have a binary classification because we have play and don't play. So it will be all the probability of negative of probability of play into log 2 of probability of play minus probability of not play into log of probability of not play. Okay. The same, this formula, I'm just created a function with respect to target column. I am finding out the unique counts. That means this probability for this probability is nothing but no number of positives divided by the total number of records, right? And this is number of negatives divided by total number of records. So I'm just getting the elements and the counts, and I'm using this exact same formula here for that range of things to find out the entropy with respect to target column. Okay. Now, since Outlook has three elements, and when we will be using a you know decision tree classifier of sklearn, we need to do you know an encoding of the categorical variable. Okay, and that encoding can be of two types. One is level encoding, and one is one-hot encoding. Okay, so we have to be very careful when we use a level encoding. Level encoding should be used before we pass on that encoded data for decision tree classifier only if the data itself internally has some ordinal nature. That feature has an ordinal nature. If it doesn't have, decision tree internally considers that when you do a level encoding, it has an ordinal nature. Hence, it is better to use, if we do not have an ordinal nature of the data, we should use an one-hot encoding. Okay. So as we know, we have three features. It will create three columns. Okay. And we need to find out which of these feature columns can be used as a root node. Basis, entropy, and InfoGain. We'll understand what is InfoGain just a bit. Okay. What we're doing right here now, So what, this is very simple. We are trying to calculate the each unique elements of outlook which is present here, and then we're running a for loop for those outlook values. We have initialized an empty dictionary for each of these entropy calculation, calling the function, and then we are putting all the values of the entropy. This is the class for each of these outlook values. Okay, because we have created a subset of that variable of each of the outlook values. So basically, from a single data set, we created three subsets, and then these three subsets have been passed with the entropy function to provide each of their entropy values. So rather than manually single one after the other we create, I'm just running a for loop here where I'm from the entire data set of Outlook, I'm creating a subset, and that subset with the subset class, I'm just passing on the class target column to find out the entropy of each of them. I hope it is very clear. Okay. So now we have got the entropy for each of these elements. And I hope you have seen before. So if you take this graph of probability of positives, okay, with entropy, so entropy ranges from 0 to 1, right? As the probability of positive increases, the entropy increases and then it comes down. Okay. So what is entropy? So entropy, as we know, it measures the purity of the split. So we know as thermodynamics in physics classes, the entropy is nothing but the randomness. For example, if we have ice, water, and vapor. So vapor has more entropy because it is more random. So in machine learning term, if there was a say I have these are my one class. Okay. Now if I change the color and I have like this. Okay. Now this is more of a non-linear and a random data. So there's a lot of randomness in the data. That means my entropy is high. It will not be able to find out the purity of the split and get and able to classify, okay, the class separately and a precise manner. So the randomness is high and hence high entropy. So as entropy ranges from 0 to 1, if an entropy, we find out the entropy of any node which is 1, that means it is the most impure split. And you will see that we are not able to, the probability of, if it's a binary classification, you will see the probability of my classifying both the classes will be 0.5. That means basically it is a not a good model, and it is trying to predict, telling my probability of having 1 and 0 in both the case it is 50%, which is not the ideal scenario which we want. Okay. I hope we got it. What is entropy and how do we are finding out the entropy? Now, entropy is not the only parameter we need to find out. We need to find out the information gain, which will help us to understand, you know, uh, which which features to be selected. As I said, we have outlook sunny, we have outlook overcast, we have outlook rain, right? Which node to be selected as a root node, that can only be provided if we find out the information gain of this entire individual splits, and the one which has the high information gain will be that splitting criteria will be used and that element will be used as the root node. Now, how the information gain is calculated? As this is the formula, we can see it's very simple. We calculate the total entropy, that is nothing but with respect to our total data of what we have 14 records. In that, how many are positives? Say, for example, we have no 6 positives and 8 negatives, for example. So we will calculate the for the total record, we will calculate the entropy basis the formula which we have discussed, and then we will minus it with the weighted. So we will do a weighted entropy calculation for each of the elements of that particular feature. Okay, and for example, what will be the weighted thing? Say, for example, in our case, like outlook sunny. So if I have uh, eight eight plays and for example, let us have a 3 play and 2 no's. Okay, so the weighted will be 5 by 14, and it will be the entropy for that particular node into the entropy for that particular node. Okay, so in our case, we have got the entropy of our sunny, right? So the entropy of sunny is nothing but 0.97. Okay, similarly, because it is a summation, okay, and negative summation of this. So if I put a bracket, this will be plus, and then again for the same for overcast, how many were records were there? So for example, if it was like 6 records, 6 by 14 into my this one, the entropy of that overcast. Okay, and then for the rain, for the rainy element, we'll have to find out. Okay, okay. So using this formula, what I did, I have just created a function where I'm calculating the total entropy here. Okay, and then I am finding out, because I need to find out for each of these elements of remember, as I said, we need to do a one hot encoding, right? So for each of these elements which are treated as a column, I want to find out the weighted entropy of this. So what I am doing is I just found out the unique values, that is nothing but sunny, overcast, and rain. And then I'm running a for loop here where I'm trying to find out these subsequent value and calculating the each entropy for them, which we have done before. I'm using the same entropy function, and then I'm finding out the weighted entropy, because I need to find out how many no total number of data is this one, and then the subset for that particular subset, what was the total number of records for particular subset, right? That's what I showed, and that I will calculate for each of these values, and then that weighted entropy, total entropy minus the weighted entropy, will be my information gain. Okay, for each of these values. Clear? Now, when we do this, so when we find out, and then for what I'm doing is I'm now computing the information gain for each value of the outlook. Okay, for that I will just use the entropy and split of this class, and then this is my gain. And if I use this if this is the function which I'm using, right? Information gain after split. So when I use this, I will get the information gain for each of the element present in the outlook. And if you see with respect to class element, okay, I'm able to find out the information gain. The higher the information gain, that particular element will be used as a root node, and we can use that as a splitting criteria with higher information gain, which is based on lower entropy and then the higher information gain of that particular split of the node. So for each element of this outlook feature, we can calculate the information gain. And internally, when we use a decision tree classifier of the sklearn library, it uses these parameters, do this computation at the backend to give us the optimum selection of the root node of the specific feature of the element of the feature which is having the lower entropy and the high information gain. Clear? Okay, let us proceed ahead. Okay, we can do the same manually. So if you see, this is formula which is used. Okay, now moving to the other feature, like now we have found out, okay, in Outlook, one of the element is giving a good information gain, but it compares in, for simplicity, we have taken just two features, right? So, but it individually compares for each elements of all the features which is present and find out which particular element of the feature gives the best, best information gain. Now, in the binary split, we are doing because for the rest, because in numerical column, the computation is expensive in case like that, because what this does it, if I have a numerical column, like for in this case we have a humidity, we need to first sort out the values of it. So for example, I've already sorted out 20, 40, 60, 80, 100. Now, which element to be selected? So what it does, it does a rolling, uh, you know, rolling average. It does. So it finds out the average between these two, then an average between these two, and then an average between these two, and then for each individual average values, whatever the values it is, right? It will take less than that value as a root node and try to compute the entropy and the information gain for each of these criteria. Once for this, once for this, once for this. Okay. Since it is a computationally pretty expensive, and that's why for simplicity of this session, what we have done is we are just bifurcating in a binary class. We are creating high humidity, which is anything more than 75, and low humidity. Okay. And then what we are doing is we are just calculating the entropy for this subclasses, passing the feature attribute. This is the target column. And similarly for this, and if you see, we'll get the entropy pretty high for both the cases. Okay. And same this function, if you do it manually, if you see, there were 9 records of out of that 5 for high humidity, like more than 75, there were 9 records, out of that 5 were positive, uh, 4 were negative, and we put the formula, we'll get the same value as this one. Okay. Similarly, for low humidity, we have total 5 records, 4 were positive, 1 were negative, and then if you put the same formula, we will get this entropy. Okay. Once we have found out the entropy, now same thing, we have to find out the information gain. Okay. So information gain, uh, in this case, because it is a binary stuff, binary class, what we are doing is I'm creating a function called InfoGain. In that, I'm calculating the total entropy. Then for each split criteria, I'm calculating the value and the counts. And then I'm finding out the weighted entropy, as we have discussed in basis the formula count I for each of these total number of records into the entropy for that particular split criteria for that value count. And then I'm also using a for loop uh, to get for each of these elements, okay, in that range of those values. Okay. And then after that, it is simple. We are doing a total entropy for the entire data set minus the weighted entropy. Okay, and when I use this formula, I will get an information gain of humidity like this. Okay, so comparing these two, we can clearly say that my outlook feature has a better information gain and a lower entropy compared to humidity. Okay, okay. So that's the first part of it where we understood clearly what is entropy, what entropy does, which is the measures the purity of the split. Okay, how entropy, basis the entropy, we calculate an information gain to find out the root node which will be used for the splitting criteria. This is the higher information gain, and we did from scratch in terms of without using the no decision tree classifier itself, like creating a function of entropy, creating a function of information gain, which is helping us to find out the for each element of this information gain. Okay, now there is still one problem with information gain, and that leads to our second topic here, which is called the gain ratio. Okay, what is this all about? So let us understand, like information gain will be more prone to select features as a root node who has higher number of unique elements. What does that mean? Say for example, I have a feature called day and I have elements like day 1, day 2, day 3, day 4, day 5, day 6, day 7. So it has 7 elements. And obviously say I have a class, it is saying play, play, not play, play, blah, 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 like this. Okay. So basically, information gain will get prone to select day and for that individual elements of this as a root node because it is a very clear class of high info gain information because it is ideally dealing with a single day whether we are playing yes or no, right? Obviously, we'll get a very low or close to zero entropy, and that's why it get prone that information gain are more prone to features with more elements, which is not the ideal scenario in our case. We should not get biased towards this because this is a clear cut case of no having element which is saying uh, play or not. We should also compare with other elements, say humidity, temperature, no, and outlook. Okay, stuff like that. Okay, so researchers find out that in order to overcome this problem with information gain, they came up with a concept called info gain ratio. What is this all about? It basically penalizes the information gain, the particular element of the feature. Okay, and how it penalizes or normalizes it, or some you can also say normalizes it with the entropy of the split entropy. That means we calculate the entropy of that particular split variable, not basis the target column. Okay, not basis the entropy of the split itself, and it is not basis the entropy of the class label or the target column. What do I mean like by that? Say for example, I have you know um, Outlook in our case example, and I have records of sunny, say 3, overcast as 4, okay, and then rain as the rest. So what I will do in this lower portion is, that is the split entropy. I will not consider with respect to the class yes or no, play or not play. Okay, I will basis the split itself. So what it will do, it will calculate the entropy, that is nothing but same uh, no summation we need to find out. So summation of negative summation of entropy for this Sunny. So the total records, number of records with Sunny is 3 and total is 14 into log 2 of 3 by 14. Okay. Then again plus within this bracket for outlook stage is just 4 by 14 into log 2 of 4 by 14. Then plus again whatever the rest amount it is, 7 by 14 into log 2 of 7 by 14. So there is a split entropy which is being calculated, and that is in the denominator. So my gain ratio is calculated by dividing the info gain with the split entropy. Okay. And higher the gain ratio, that particular feature element will be selected as the root node, and it will then the best splitting criteria. Okay. And we will do from scratch and find out how we can be done. Let us see how we have done this. So what we have done is very simple. We have, okay. So this split entropy is also called as intrinsic info. Okay. So what we have done, I created a function called intrinsic info, passing the data and the split attribute name what we are giving, finding out the unique elements. Like for example, under Outlook we have Sunny, under Sunny how many unique records are there, that we are finding out. Okay. And counts we are finding out. Under rain how many records are there, that we are finding out. And then just this is the formula of the entropy again, and division by 0 we are doing for counts in counts. That means we are running a loop into that. Okay. This is nothing but calculating the split entropy. And then we are doing a gain ratio function, which is nothing but I am passing the getting the information gain with respect to the class. Okay. And then dividing by the, I am calculating the intrinsic value, calling this function. And then what I am doing, I am using this and dividing information gain and divided by the intrinsic value. And this is just a division by 0, uh, taking care of the division by 0 issue so that we do not get an error. And then I'm calculating the, this function will help us to get the gain ratio. Okay. Okay. Moving ahead. Now let's calculate the gain ratio for each of these element of Outlook and also for the humidity. It is simple, the same what we have done. We are taking out this, we are running a for loop for each of these unique Outlook elements. We are using the gain ratio function to get it the gain ratio outlook, for example, and also for humidity, as we have for simplicity we have taken binary condition. We are doing anything more than 75, less than 75, and again using the function to calculate the gain ratio. As I said, the higher the gain ratio, the better that element will be used as the root node. Okay. And because it's a normalized gain ratio is nothing but a normalized info gain, and that can be used for our splitting criteria and selection of the root node. And here also we will get the same information here. Okay. So let me summarize quickly before we will see a visualization of the tree having all the elements. So what we have learned here is we have seen how we can from scratch how internally a decision tree classifiers use all these splitting criteria and the computational it does in terms of finding out the entropy for each element of the features, and then permutation and combination of finding out different elements of those features, selecting different elements of these features at the root node and finding out the information gain basis the entropy. So I hope you can understand that internally it does so much of mathematical calculation, and hence entropy is not recommended to use for a large data set because it is computationally expensive, because uh, we are using a log calculation there, right? So in this session, we'll understand about entropy, but for larger data set, we should use Gini impurity or Gini index. But in this session, what we are trying to find out, like how from scratch internally the computation is done to just to find out what is the best splitting criteria and what feature element should be used as my root node. In summary, internally it calculates the entropy for each level of node, for each level of element of a categorical column. Okay, and then for each element of those categorical column, as it will be one hot encoded, it is considering each element as the root node, the information gains are calculated, and then finding out the best element which has the highest information gain, which will be used to compare for other feature. In our case, there was a numerical feature, right? So the numerical feature, there the computational of entropy is little cumbersome, because what it does, it sort the data and then it is a rolling average, and then for each average value it try to select that less than equal to that average value as the root node and find out the same process computation it does. In our case, what we did for simplicity, we took a binary split in terms of, we took a threshold value of 75, and anything more than 75 as a high immunity, so that we can understand easily that this is how it internally does for each values, finding out the rolling average for each of these values, and then try to calculate the entropy and the information gain. Ultimately, what it will do, it will compare the information gain for each features, both categorical and numerical, and whichever gives the highest information gain will be selected as my parent node or the root node. Okay, as we also discussed, that there is something called a gain ratio, which is there to penalize for the features which high number of elements, because InfoGain try to uh, get biased or uh, you know get prone to elements features with high elements. That's why we penalize it with a split entropy. The information gain is divided with the split entropy to get the gain ratio. So anything which high gain ratio is my best splitting criteria, and that element will be selected as the root node. Okay, let us proceed and quickly see uh, a visualization of the decision tree using the decision tree classifier and the plot underscore tree functionality, which is there under the sklearn library uh, of of tree. Okay, if you see here in this case, what we have taken as independent features three element outlook, humidity, and windy, and we are, because these two are categorical features, we are doing a one hot encoding as we have discussed before, and then we are bifurcating target column as class. We use a decision tree classifier and use a criteria entropy, fit the model, and then we're just plotting the model. Okay, once we plot the tree, what we do is, if you see here, just a second, this is a fully grown tree. So we are, it is highly overfitted for sure, but because we have not used any of the pruning technique here, that we will understand in some other session, like pre-pruning and post-pruning technique. What you are trying to do here is, it selects the information gain and try select those particular features which has the high information gain, internally does the calculation and try to split it and go to this terminal node. These are called the leaf nodes. Okay, this is my root node, and it has, because we have taken humidity, uh, it has taken humidity as one of the features, and we have taken all the elements. So we have taken entire data set. So internally it has calculated the rolling average and find out this, which is giving uh, the high InfoGain and selected this as a root node. And then if you see total record, the 5 and 9, and then it keeps on splitting. So 9 records out of that, 2 are non-play, 7 are play. Okay. And then again, 3 and 2. So it is trying to split it until unless it gives me the pure split where the other class is totally zero. Okay. If you see here, this is zero, this is zero. This is my leaf nodes. Okay. This is actually, if you see the entropy is 1 because the value are both are 2. Okay. This is my leaf node. Okay. The other class is 0. Okay. This is how easily we can understand how the data, and now once the new data come, it will follow that path. Okay. This is yes, this is no. So any humidity which is less than 82.5, which will follow this path, and then again it will take the criteria. If this is yes, so if it's the rain outlook and it is less than zero point 0.5, what that mean is it is either rain yes or no, right? So it's less than zero point 0.5, that means no. Okay, if it is no, then it will go this path. If it is yes, then it will go this path, and then again it will split accordingly. Okay, so this is how easily, that's why it is called a nested if else condition. Okay. Okay. So I hope it is clear. Thank you guys for your time. Thank you.